Hey everybody, what's up? Welcome back to another exciting day of proof set theory and logic. Today we're talking about functions. Let's talk about functions. We started last time. Here's the idea. Here's the setup. So, what do we got? We got some blobs. We got a blob A. We got a blob B. These are sets. Okay. We got some sets full of stuff. And here's the idea. A function is just a particular way of drawing arrows from one set to another. And arrows, quite specifically, as opposed to just lines, since the notion of a function has an implicit ordering to it. That is, you put something in, you get something out. This is how it's kind of classically presented to you. And there's a distinction between the input and the output. One thing comes first. The input comes first, then the output comes after, right? So there's an innate kind of ordering in functions. All right, here's like the sort of different ways you could do things. If you start, trying to pick some sets of stuff and going like, okay, here's some sets. I could draw some arrows between things. I could do stuff like this. This is not a function. You might look and say, okay, you have drawn some arrows between stuff, but there's some stuff here that doesn't have arrows going out of it. Yeah? Okay. So in the cases where everything has an arrow going out of it on the left-hand side, we're going to call that a function. That's going to be the definition of a function. So I will quickly, write that over here. And I will write it in exactly the same way it appears in your note packet. Definition. Let's let A and B be sets. A function f from A to B is a relation from A to B with the property that for each A in A, there is exactly one ordered pair in F for which A is the first coordinate. Okay, that seems a little bit weird. What exactly does this mean? What it means is exactly what we said over here. So if we write this in ordered pair notation, what this says is that our function f, which we're drawing here as the thing sending A to B, that's what these arrows are encoding, f would be just the set 1, B, 2, C, and 3, D. Notice what this is saying, the condition that it's a function, is that for every single thing in A, it appears as the first item once and only once. Exactly one time. Does that make sense? Seems maybe like a kind of idiosyncratic condition, but it is a very useful one. Okay, now how could we make this not a function? What could you do? Tell me an arrow you could draw to make it not a function, just to make sure we all got it down.
From 2 to 8?
Yeah, let's take 2 to A. Okay, if we did this, then we would have this would be bad, since I would have 2 as the first coordinate more than once. Now, f is not a function. Okay. So you can see how things could fail to be functions. You could either have too many ordered pairs with something the same at the beginning, right? Or you could lack an ordered pair. That is, of the correct answers to how do you make this not a function, that was one of them. There are many others. You could pick, 1A, 1C, 1D, 2B, 2A, 2D, 3C, 3B, 3A. You could do those lines. Or another good way would be just to get rid of one of the lines like we had it originally drawn. If we do this and we get rid of 2c, now f is also not a function. Now we just have 1b and 3d. Now f is instead a what you might call a partial function. So a function on a subset of A. That is, if we pretended A only had 1 and 3 in it, or we looked at that subset of A, then this would be a function, right? Okay, so there's a couple of parts to keep track of with functions. I'll make this back into a function again by putting 2c in there, and I have 3d still, all good. Now, there are a couple of pieces to keep track of. What's on the left? What's on the right? Those are the two easiest ones. Okay, the set A is called the domain of F, and the set B is called the codomain. Okay, so the codomain is the companion to the domain in the function. Seem reasonable? There's two sets, one on each side. One of them's at the back of the arrows, one of them's at the front of the arrows. Okay, cool. Domain, codomain. Notice, codomain, different from range. That is, you probably have seen the range of a function, as in, like, what stuff do you get out? What is the range of this function? Just for an example here.
B, C, D.
B, C, and D. Those are the things that actually get hit. It is not all of B. Okay. This maybe motivates a pretty reasonable thing you could start to think about. You could say, hey, when is the range, the stuff that gets hit, the same as the codomain? That is, when does everything get hit? This is a nice kind of classification of a function. And you can pretty easily kind of see, I guess, that there are, in a big way, two different things, two different kind of classes of functions that you might care about more than others. Of course, there's like an almost unlimited number of potentially different like conditions you could impose. You could make up your own condition and be like, we'll call a function whatever name you want to give it if it satisfies whatever condition you want to make. But there are two that arise very naturally. These are injectivity and surjectivity. So surjectivity is the case where everything gets hit. This function is not surjective. Injectivity is the case where everything that does get hit gets hit only once. Why would we care about these two things? Let me ask you a question quickly. I will erase this and redraw another one. Okay, so if we have a function from A to B, let me put okay, if we have a function from A to B, when do we also have a function when we reverse the arrows? Now, if I drew it like, say, like this, we certainly don't have a function when we reverse the arrows, right? That is, if I squiggled my way on over and made a B and an A over here, and we went, okay, I got A, B, C, D, and I have 1, 2, 3, and 4, and now I go from A over to 1 and 2, and I go from C over to 3, and I go from D over to 4, you'd say that this is not a function, and it's not a function in multiple different ways, right? What are the ways that it fails to be a function? Well, B doesn't get sent to anything. And A gets sent to two different things. Uh-oh. Okay, so I guess what I'm saying is that if you have a function, there are, or if you have something that's not a function, there are essentially two ways it can fail to not be a, or fail to be a function. The tongue-tied. There are two ways it can fail to be a function. One, it could not send something in the domain to something in the codomain. Okay. The other way is that it could send something in the domain to multiple things in the codomain. There are two different types of problems that can happen that can prevent something from being a function. Now, if you look at a function and you say, what if I reverse the arrows? There are two different types of ways that you could fail to get a function. This suggests a characterization of functions into essentially three nice classes. Functions where if I reverse the arrow, I don't get a function. And then, or maybe even just two, I would say, or three nice classes. Functions where if I reverse the arrows, I get a function. And then functions where if I reverse the arrow, I don't get a function, of which there are two ways to do that. And you could fail in both ways, as we see right here. But you could also just fail in one way. Like, for instance, let's suppose that b is not even part of this. Then this is still not a function, but it is not a function in only one way. That is, something gets sent to two things. Okay, on the other hand, if instead I still had b here, and maybe instead I get rid of, say, like 1, right? If I didn't have 1 right there, and instead let me think about how to write this right. I want to make sure that I am going to do a good job here. Maybe I do have 1 there. I'm going to come up with a new example right here. So here, yeah, I'll just even get rid of 1. That's just going to be fine. Okay, if I get rid of 1, then I still do not have a function, but I do not have a function in the other way. That is, now I don't have a function because something fails to be mapped over. Okay, so these are the two big classes of functions you'd care about. And why would you care about them? Well, because much of the time you use functions, what you are interested in is solving some kind of an equation involving a function. That is, most of the time you use functions, you are trying to do something like f of x equals y, and you want to figure out what x should be. Yeah? This is like when you're, factoring a polynomial, you're finding the roots of a polynomial. You're setting a polynomial function equal to 0 and trying to find out what values you can plug into the polynomial to get out 0, right? Solving any equation really boils down to something like this. It says, hey, when is a function equal to something? Okay, so if we want to find out when, then we need to effectively undo the function, at least partially, at least in some way. Yeah? Now, I'm kind of drawing this out and not writing a lot of definitions because I want to motivate what we're going to define. But here's kind of the way you can break down these two different sort of scenarios. I'll show you how each one of them gives you different things, and then together you can get something nicer. So let me go A, B, A. So if I have a function f here, and I go, say, maybe let me make this a little bit bigger. And then A, B, C, just A, B, C, how about? I'll have 1 go to A, I'll have 2 go to C, I'll have 4 go to B, and I'll have 3 go to A. Can you come up with a way to get back to what you started with? That is, to follow the arrows so that you end up back where you started. Well, I can certainly follow 1 to A, and then I can follow A back to 1. I can follow 2 to C, and then I can follow C back to 2. I can follow 3 to A, and then, oh no, now if I try to go down here, I no longer have a function. If I follow 4 to B, I can still take B back to 4, but I would fail to be able to get back to where I started with a function. That is, the only way I can get back to where I started, where I can follow my arrows to go back to where I started from, would be to have something that is not a function. Does that make sense? Okay. While on the other hand, if I had something like, say, for instance, let me take this out right here and remove 3. I'm going to throw a D in there. Okay. Now if I had something like this, notice I can go from 1 to A to 1, 2 to C to 2, 4 to B to 4. And indeed, while D doesn't have anything going from it, I could draw an arrow from it to anything that I want over here. Pick anything, right? Let's send D to 4. Who cares? Is this set of arrows a function? Everything from B to A, well, everything in B has only one arrow going out of it. Yeah? Okay, cool. It's a function. It has one and only one arrow going out of everything in B. So what this tells you is that when you have the nice property that everything in A gets sent to something in B, and if something from A hits something in B, then that is the only thing that hits it, then you can generate a second function, let's call it G, such that if you go through them, you get back the identity function, the function that sends an element to itself. Yeah? That is, if you want to write it in regular function notation that you're probably used to, if f of x equals f of y implies x equals y for a function f, then there is a function, I'll say f from A to B, then there is a function g from B to A, such that, well, I take f, I punch an x through it, then I take the result and map it back to A, and I get x. Okay, so if you thought about like invertibility before, which I'm sure you have since you've taken algebra, right? This almost looks like invertibility. What it is it is left invertibility. I have a function that I can put to the left of f to get back the identity. I do not have a right inverse. Think about this. That is, if I want to go the other way and take, now I will draw it this way. Okay, so now I have A, B, and B, and now I go 1, 2, 4, A, B, C, D, and I just map it over in the usual way, 1 to A, 2 to C, and 4 to B. Then if I go A, B, C, D, another copy of B, if I want to go from here to somewhere where I'll get back to A, well, I can do that just fine. I can take B to somewhere where I'll get back to B. I can take C to somewhere where I'll get back to C. But can I take D to anywhere where I'll get back to D? No, I can't. That is, if I wanted to draw an arrow so that I could go follow it along and get back to where I started, I can't because nothing from here goes to there. So what I'm showing you is that this condition right here is not enough to get a right inverse. That is a function that you can put inside your function, something you could do first to end up back at the same place you started. So what I'm trying to, I guess, make clear is that left and right invertibility are different. Yeah? Now, what gives you right invertibility? Well, I would say that this example makes it relatively clear. You certainly have to hit everything in B. The fact that D is left out is the big problem. So let's look at an example there. Let's go this other direction, and let's see what gives us right invertibility. And can you guess? It's going to describe effectively the other way that something can fail to, or that a function can fail to induce another function if you flip the direction of the arrows. So let me draw another example, and I'll show you how you get right invertibility very nicely. from the other condition. So if you have, say, A again and B again, you could say, all right, actually I'll even go like this. I'll go draw my 3 boxes here. So I'll start here with A and B. And maybe A has just 1, 2, and 3, and B has A, B, C, and D. Or no, I'll go even more like this. I'll do A, B, and C, and I'll go 1, 2, 3, 4. There we go. This will be better. So I could have a function that looks like, say, this. That's a function, isn't it? It's a function since every element of A has one and only one arrow pointing out of it. It's a function. All right. Now if I redraw B over here with A, B, and C in it, can I come up with an arrow so that when I follow it over and then I follow the next arrow, I get back to where I started? Well, I could take A over to, say, 1, and that brings me back to A. I could take B over to, say, 4, and that brings me back to B. Yeah? Where could I take C to? I could take C to 2. And that takes me back to C. Yeah? So there is a function G here such that if I do G first, and then I run the result through F, I get back the thing I started with. This is the opposite condition of that one. It's with the F and the G reversed. That is, it's got something that you can put on the right of F to get back the identity, the function that sends a thing to itself. Okay, so this is actually maybe weird if you've thought about inverses just purely in like a, a nice commutative sense, like, if you multiply 5 by 1/5, it doesn't matter whether you do it on the left or the right. Yeah? You get 1 either way. Yeah? For functions, there is a very different notion here. There's a big distinction between a left and a right inverse. That is, a function could have a left inverse but not a right inverse but not a left inverse. It could have neither, or it could have both. Oh, interesting. By the way, what is the condition that we have just seen here that tells us there is a function g such that we can do this? Remember, here, for a left inverse, what we needed was that everything that got hit only once. That is, if f of x is equal to f of y, then x is equal to y. There are no two different things that get mapped to the same thing. Yeah? What is the condition we need here to get something we can plug into f to get back to where we started?
If g of x equals g of y implies x equals y.
Oh, that is very clever. You're trying to say that, well, the right invertibility of f implies the left invertibility of g. That is clever, and that is true, but we shouldn't use g to reason about the existence of g. Yeah? That is a good idea to say, well, it's just the exact same condition, but now on g. But we don't know if such a g exists right away. What condition on f tells us such a g exists? So before, we had some things on one side being hit more than once. That ruined it. Here, what can ruin it? Well, we saw it from the previous example. It's some things not getting hit, right?
Surjectivity.
Yeah, exactly. This is called surjectivity. That is, the other way around says, if for all, I'll write it this way, y in B, there exists x in A such that f of x equals y for a function f from A to B, then there is a function g from B to A such that f of g of x is x. So right invertibility means you have to hit everything. Yeah? Putting it all together, what we're seeing here is that the two different ways that you can fail to have a function when you flip the arrows on a function describe two nice classes of functions, right? That is, they describe when a function is left or right invertible. Do you see what I'm saying? Okay, this is like a whole lot of hand waving and trying to lead intuition and stuff like that, but when we introduce these things, I think a lot of the time they're just presented as like, here's this thing called injectivity, here's this thing called surjectivity, and people go like, why? What the heck is this? And it all comes out of a super easy and obvious question, which is, hey, when I draw a function, I have to draw like the little points on my arrows. Why? Why can't I just not care about the direction of the arrows? And the answer is you can not care about the direction of the arrows, but it means that one way might be a function while the other way might not be a function. And we can categorize the way that the backwards direction could fail to be a function. And those categories actually tell us something insanely useful when a function is or is left invertible or right invertible. And notice, when you have both, then your function is genuinely invertible. Kind of nice. But hey, here's something to notice. Here, our g goes from b to a, or let me make sure this is right, yeah? Yeah, b to a, and this takes us from b to a. Okay, yeah, good. All right, nice. Going too much about it. We'll talk about this in a moment. Here, let's just do some definitions. I don't want to throw too much up there. Let's make sure that we've got some good understanding of functions. Let's categorize them, and then we'll see the consequence of this sort of initial ramble, right? What are left and right invertibility all about? So, on to the next bit. Let's do a big example. Can I keep this little string from falling over? All right, examples. Okay, consider the sets. Let's take A to be the set 1, 2, 3, and 4, and B to be the set 1, 3, 5, and 7. Define the following relations from A to B. Okay, let's make a few of them. I'm going to ask you whether these are functions. So let's have f be 1, 3, 2, 1, 3, 5, and 4, 7. Is this a function? Okay, good. Here, I'll just write them all out. The question is going to be, are they functions? Okay, and then we'll ask more questions about them. So G, let's have G be 1, 1, and 3, 3. Let's have H be 1, 1, 2, 3, 3, 5, and 4, 1. Okay, let's take J, a weird one to use for the name of a relation, but why not? 1, 1, 2, 3, 3, 5, 4, 7, and how about, say, 2, 7? And let's take 5 to be, let's call it Pat. And let's be 1, 1, 2, 3, 3, 5, 4, 7, and 1, 1. Which ones of these are functions? So which are functions? Okay, so A has 1, 2, 3, and 4. Yeah? Here's all you have to do to check. You go through each one of them and you make sure that 1, 2, 3, and 4 all appear as a first element in an ordered pair. Each of them appears once as a first element in an ordered pair, but only once. So let's go through and check. I've got 1, I've got 2, I've got 3, I've got 4, and there are no repeats. This is a function. Check. I've got 1 and I've got 3, but I'm missing 2 and 4. Not a function. Yeah, okay. I've got 1, I've got 2, I've got 3, I've got 4. Yes, a function. I got all of A. Okay, here I've got 1, I've got 2, I've got 3, I've got 4, and I've got 2 again. That is, I've got 2 here, and I've got 2 here. Not a function. Every element of A appears as a first coordinate, but there's an element of A that appears more than once. No good. Okay, here I've got 1, I've got 2, I've got 3, I've got 4, I've got 1 again. Uh-oh. Uh-oh. Not a function. Okay, so the answers are 1 and 3. All right, so yes.
Out of curiosity, the last function is like just.
Oh, wait, I've made a mistake here. This is a 1 again. This is a function. Sorry, I thought that was something else. Thank you, thank you. You are right. This is a function. Why?
Because it doesn't care about replicates.
Same. So that is a function. Made a mistake going too quickly. Thank you. Good point. Yes. Okay, good. 1, 2, 3. 1, 3, and 5 are functions. That is the answer. 1, 3, and 5. Yes. That is a good, subtle distinction. Hopefully everyone caught that. And if you didn't, then it's great that a mistake was made because hopefully that drew extra attention to it. That is, remember, sets don't care about duplicates. That is, this set here, to be clear, is exactly the same as the set 1, 1, 2, 3, 3, 5, if I can write, and 4, 7. That is, that duplicated 1, 1 doesn't need to be there. They're the same set. Sets are only about what stuff do you have, not how many times do you have it. Cool? Cool. Functions. All right. Now, if we look at these guys, and we say, hey, which ones of them do we get functions from by reversing the arrows? Well, let's just flip the ordered pairs around. That is, if I flip the ordered pairs around, which ones are functions when you flip them? Let's go through it and find out. All right, so in B, I've got 1, 3, 5, and 7. Okay, here I've got, let me use a different color to make this clear. And now I say, hey, look, I've got 1, I've got 3, I've got 5, and I've got 7. All of B. So that one's good. 1 is indeed a function when you flip things around. Yeah? Okay, what about 2? I've only got 1 and I've only got 3. I'm missing 5 and 7. Not a function. Okay, what about 3? I've got 1, I've got 3, I've got 5, I don't have 7, and even worse, I've got 1 twice with different things next to it. Not a function, and not a function in 2 different ways. Okay, what about 4? I've got 1, I've got 3, I've got 5, I've got 7, but I've got 7 again and 2 different things next to it. Yet again, not a function. Okay, what about Pat? I've got 1, I've got 3, I've got 5, I've got 7, And notice this one is extraneous. We've already got it over there. Yeah? So I have 1, 3, 5, and 7. It is a function. Nice. So this really shows that you can get like the whole breadth of possibilities. What ones are functions when flipped? The answers are 1 and 5. Okay, cool. So, functions. When can you flip them? Splits them into classes. It is not the case that whenever you've got a function, you can flip it and get a function. It's also not the case that whenever you don't have a function, you can flip it and get a function. There is more, there are more idiosyncrasies than that. So, moving on from this example, let's look at some other kinds of functions, perhaps ones expressed in a nicer and easier way to see than these ones, more familiar examples. So here's another example of some functions. So, define the following relations from R to R. Okay, here's one. Let's let f be the relation of x's and y's such that x is in the reals and y, I'll say it this way, and y is equal to x squared. This is the ordered pair way to express the function f of x equals x squared. Right? Okay. What about, say, g? Let's just do it the other way. X's and y's such that x is in R and x is equal to y squared. Maybe I should even say y is in R. How about that? And x is equal to y squared. Or even, no, let me say x, how about? Let's just do that. Yeah, there we go. Because that tells us what y we'll get, yeah. Okay. So, which of these are functions? Okay. Then, f is a function. But is g a function? You can kind of imagine. No. Why?
Because, like you can plug in two y values and get the same.
Yes. In fact, g is not a function for multiple reasons. For instance, you're saying you can plug in
Two different y values.
and get the same x. Okay, yeah, right on. I see what you're saying. Okay, so you're viewing it like you're plugging in your y and you're getting your x. Okay, so you're saying like you could have, say, like 1, 1, and 1, say, minus 1. Both of these are in G, right? Also, notice, I'll say, there are no elements x, y in G for which x is less than 0. So it actually fails to be a function in both ways that it could fail to be a function. Both by failing to map everything in the reals to something, and by mapping some things to multiple things. So it fails both ways. Not everything has an arrow pointing out of it, and some things have more than one arrow pointing out of them. It's bad in both ways. Okay. What if we flipped G? Is it a function now?
Yes.
Would you think so? If you flip g, do you get f?
So like you flip the ordered pair as well, or like?
Oh, if you flip like, yeah, if you just flip all the ordered pairs in G, do you get back F? Do you think so? Yes or no? Maybe people are getting unconfident of themselves here. Okay, so what kind of things are in G? Everything in G is of the form, let me just write it this way, y squared y, right? Whatever y is, it'll be the second coordinate, and whatever the first coordinate is to satisfy this has to be equal to y squared. What are all the things in F? Well, they're of the form x, and then whatever y is, it has to be equal to x squared. So if you flip all of these things, do you get all of those things? Why? What are you saying? What are you thinking? Just kind of guessing, right on. Okay, so I think just intuitively, if you flip this, you have a thing and then a thing squared. It looks the exact same. I think the thing people are wondering about is there's somehow something, some type of y that you, like some sort of a restriction on y hidden in here, right?
Can y be less than 0?
Indeed, as we see right here, yes, y can be less than 0, right?
Yeah.
Yeah. Are there any y's that you can't get? No, right? Pick a y, pick any number you want, yeah? Okay, all you have to do is square that number, and that is the x that goes with it, yeah? So for any possible y you want, there is some x that goes with it. Hence, there is some xy in G. And so we have no restrictions. That is, if you flip G, you do indeed get F, right? Okay, cool. Nice. Fun. So we see the ways that we can fail to have a function, the ways that flipping things can go wrong. We see the ways that we can have a function. Kind of nice. All right, cool. So it can be the case that you have a non-function that when flipped, you obtain a function. Yeah? It can also be the case that you have a function that if you flip all the ordered pairs, you get not a function. And there are multiple ways that that can happen. Okay. Now, let's break for a second and look at this. Does this seem like a really unnatural way to write the squaring function? Yes. Okay. So this, I guess, motivates the classic notation, which we will now sort of revisit. I suppose it's worth writing out formally. But it is, there's my rag. It is good to start, I think, by trying to the spray bottle is constantly running out on me. I think it is good to try to start by looking at everything outside of this overly, I don't know, kind of mechanical idea of like a function is a thing to transform one thing into other things. And instead say a function is a way to associate things. That is, it is a way to select ordered pairs. So a function is just a collection of ordered pairs, things you put in, things you get out. But from that, the immediate, it immediately suggests the classic notation. That is the classic notation of there being like a little f of x device where you put the f in, or the x in, and the f gives you the y, right? Is a perfectly reasonable thing to say. So, notationally, we often write a function f from A to B as f colon A to B. I.e., we say a function has two things. It's got a domain and it's got a codomain. Those things are different, right? So we're going to write the name of the function, and then we're going to put a colon to separate it out and say, this part isn't part of the name. The rest of it just tells you the domain and the codomain, and we separate the two of them with an arrow instead of a comma because it's more suggestive, right? It kind of more clearly gives you that idea of like, stuff here is going to there. This is the first thing, that's the second thing, yeah? Arrows kind of have an implicit ordering in them. They start at one part and go to the other part. One part seems more first than the other part, yeah? Okay, cool. We will often write a function, so it'll be and denote xy is in f by writing f of x equals y. That is, f of x equals y just tells you that xy is a pair belonging to that relation. So anytime you see f from A to B, this is telling you that you have a collection of ordered pairs, first thing in A, second thing in B, satisfying the very nice property that everything in A appears as the first coordinate, the first thing in one of the ordered pairs of that, and it appears in only one of them. Okay, cool. Functions. Good? Next time we'll revisit what we talked about at the beginning. Injectivity and surjectivity will characterize the ways that a function can succeed or fail to be right or left invertible. That is, the way a function can succeed or fail to have another function when you flip the direction of the arrows, or to induce another function when you flip the direction of the arrows. But we'll do that next time. And yeah, see you around. Have a great day. Don't forget about the homework.